Okay, class, welcome back. So, in the last videos, we talked about finding the pH of a strong acid, and that was quite straightforward because of the fact that the strong acid is 100% ionized, right? That all of the original acid is converted into hydronium ion, and so fundamentally, that is the only source of hydronium ion that we need to worry about. Now, weak acids become a bit more complicated because while there are still two sources of hydronium ion, right? Remember, we have some hydronium acid from the acid, of course. So from the acid ionization. And we have some from the water, right? The autoionization of the water. Now, again, in the strong acid, we could principally ignore number 2 because we were getting so much hydronium from number 1. But in a weak acid, since this is much more of an equilibrium, right? We only get partial ionization. We have the following type of equilibrium going on. And so, depending on the size of the equilibrium or how product favored the equilibrium is, right, we may get very little hydronium from this part. And so at that point, maybe, this becomes, much harder to identify. Now, still, the amount from the water isn't going to be a huge idea that we have to really build it in, but we certainly can't just look at the original concentration of the acid and straight know what the hydronium is. We have to deal with an equilibrium. And this is where what we learned last chapter comes into play. So we are going to solve these weak acid pH problems by doing equilibrium problems. And so that means going through the processes we learned for doing equilibrium calculations in the last chapter. So we're going to follow this basic protocol. We're going to use our, ice, or what you might call a rice table. Right? The book uses ice. I will sometimes use, right, where we have the reaction. Remember? So this is going to be, we're going to write out our equation, our reaction for the acid, and that'll help us guide our ice table, right, where we have the initial concentrations, we have the change, and we have our equilibrium. And in all of our problems here, our target, right, is the equilibrium concentration of hydronium, because that's what we're going to allow us to calculate the pH from. And so we're going to set up our ice table from the reaction of that ionization of our weak acid. Right? And so our equilibrium expressions here are going to be, our Ka expressions. Now, the nice part about this is that a lot of these are the same, meaning that our Ka always has fundamentally the same kind of idea, in that it always has hydronium ion concentration on the top, along with whatever the conjugate base of our acid And on the bottom is going to be the concentration of our weak acid. And so the Ka will always have this basic expression, and what's going to change is what HA and A minus is. And so we can use this, equilibrium expression, apply it to our specific acid equilibrium problem with the specific value of Ka, solve our equilibrium problem using our ice table. And once we get that, again, the key value is the hydronium ion concentration, we can solve for the pH. So that's the basic approach. And in a follow-up video, I will work some sample equations, sample problems going through this process. Now, an alternative or another way that we can look at the strength of an acid, besides calculating its pH, is something called the percent ionization. So, the percent ionization is simply looking at the percentage of acid molecules that ionize when put into water. Right? So, the Ka is one way that we look at that. Right? And we can think about it that way. The percent ionization is another way that we look at it. And of course, the higher that percent ionization, the stronger the acid is, right? Again, almost all of these we look at will be weak acids, right? Because we're talking about weak acids now, but again, there's a scale, right? We have stronger weak acids, we have weaker weak acids. And again, it's about sort of figuring out where something is in that scale. And so percent ionization is another way that we can use to characterize the strength of an acid. Now, something else that we might be interested in doing is looking at a mixture of acids. So if we have a mixture of acids, we can have a couple different types, right? If we have a strong acid mixed with a weak acid, then we essentially ignore the weak acid and we calculate it as a strong acid and we determine the concentration of hydronium and the pH based on the weak acid concentration. Right? Because that complete ionization of the strong acid provides a lot of hydronium. Now, we're going to think about back to, and a lot of this, Le Chatelier's principle. So if we remember, right, we've been working with this equilibrium here, this acid plus water goes to H plus A minus. And so remember that if we have this strong acid, it's producing a lot of hydronium ion, that's going to shift this weak acid equilibrium. Right? So this is the weak acid here, the weak acid equilibrium. It's going to shift the reaction this way. Right? So again, shifting it even more back to the reactant, so lowering how much it's ionized. And so then, again, even more minimizing the hydronium that's produced from the weak acid. So again, making it even a better approximation, or if you will, assumption that we only have to worry about the strong acid. So this kind of mixture, we're going to just treat it as a strong acid essentially to calculate the hydronium and the pH. If we have a mixture of weak acids, generally speaking, we can do something similar. And generally, we only need to worry about the stronger of the weak acids. Now, how do we know which one's stronger? Well, this again, we can look at the Ka value is probably the easiest way, or the pKa values, right, to pick out the stronger of the two weak acids. So looking for the, larger Ka value or the smaller pKa value, and just solve it based on the hydronium ion that's produced from that stronger of the two weak acids. And the rationale is very similar in that stronger weak acid is going to produce more hydronium. It's going to push the equilibrium of the weaker weak acid even further to the reactants. Again, emphasizing the importance, or the fact that we can use just the stronger of the two weak acids to calculate the pH. All right, and so again, in follow-up videos, I will look at example problems for percent ionization and solving for the pH of a mixture of acids, along with doing some weak acid pH problems.